Welcome to this episode of Transparent Physics, where we'll be talking about the three flavors of nuclear radiation. And speaking of flavors, today's flavor is lemon lift. So, all right, let's get started. So, three flavors of nuclear radiation. As a review, nuclear radiation is matter and or energy ejected from an unstable nucleus in an attempt to increase its stability. Now, in the early days of studying radiation, one of the scientists involved in that process was Ernest Rutherford. And Ernest Rutherford, as he was experimenting with radiation, discovered that not all radiation obeyed the same properties. There seemed to be different types of radiation mixed into this new invisible energy sort of thing that they were discovering. And he noticed that depending on the substance, some radiation passed more easily through substances than other radiation did. So he actually ranked, he ended up discovering he ended up categorizing three different types of radiation according to their ability to transfer through materials. And he ranked them from the least penetrating to the best penetrating. And he used the Greek letters of the alphabet. He just used the first three letters of the alphabet, so alpha, beta, gamma. So the reason we call them that is simply the order in which he felt they penetrated material. So alpha particles, as he called them, were blocked easily. Beta was better penetrating than alpha. And then gamma was extremely penetrating. So he alpha, beta, gamma. So what we're going to do is we're going to talk about these three types of radiation. Again, he didn't really know what the stuff was at the time. He just studied how well it penetrated. So we're going to talk about each of them. We're going to talk about them a little bit out of order, but you will understand why once we are done. So let us begin. All right, the first one is the alpha particle. Alpha particles are basically the heavy hitters. They are very massive compared to all the other types of particles or anything that get ejected from the nucleus. And it's a chunk of the nucleus itself that's ejected at a high speed. If we were to stop and analyze what that particle was, we would see that it's made up of 2 protons and 2 neutrons. And if you are a elementaphile, you would know that 2 protons and 2 neutrons gives you helium. All right, it's the helium nucleus, so there's no electrons associated with it. It's just 2 protons and 2 neutrons. Helium has an atomic number of 2. Now, if we summarize it in terms of just sort of symbolic representation, when we talk about nuclear reactions, nuclear decay reactions, we'll talk about this a little bit further. The idea here, the number on the top represents the atomic mass, which is the number of protons and neutrons. The number at the bottom is usually referred to as the number of protons. In this circumstance, I kind of like to associate this number as the associated charge. So the alpha particle has 2 protons associated with it, so I like to consider that as a +2. Again, that'll become a little clearer a little bit later on when we talk about nuclear decay reactions. So you can use helium, or you can use the Greek symbol alpha. Either one is fine, and that's sort of the representation that it would show up in terms of a formula. The ability of an alpha particle to penetrate substances is very, very weak. You can literally stop an alpha particle with this sheet of paper would be more than sufficient to stop an alpha particle. Alpha particles cannot get through stuff very easily at all. Again, they're a pretty big substance, and they are stopped pretty much upon impact with basically anything. Now, that doesn't mean that they are not something to worry about, because associated with this poor penetration is the fact that it's got a lot of energy associated with it. It's positively charged, so when it hits a material, it imparts a lot of energy to that material. It also has the ability to ionize very, very well. Ionization, we talked about the word ion when we talked about our atomic basics. ions are materials that have gained or lost electrons. So the ability to ionize, or its ionization ability, is very, very high. It can definitely take electrons away from the target that it hits, and that process of taking electrons away can damage the target atom or molecule in ways that we'll talk about in a little more detail in the future. Just know right now that ionization is bad in terms of damage. It's considered direct ionization because the alpha particle interacts directly with the substances that it is ionizing. And again, generally speaking, alpha particles, even though they have very low penetration, is very dangerous to human tissue. And again, more to say about that, not in this video, but it is important to note. So alpha particle, nothing to shake a stick at. It's a big chunk of nucleus that flies out, causes a lot of damage when it hits, but it will not penetrate deeply into a substance. The second one, and if you listen carefully, you may occasionally hear me screw this up. Alpha is an alpha particle. Gamma is not a particle. Gamma, and again, we're going to go to the third one next. Gamma is sometimes referred to as a gamma ray. A little more technically, sometimes it's referred to as a gamma photon. Photon, if you're a little more science literate, a lot of people associate photons pretty much just with light. A photon can be associated with any range in the electromagnetic spectrum. So we can call this a gamma photon as well. I'll probably say gamma ray. Occasionally, if you hear me screw up, I'll say gamma particle, but it is not a particle at all. There's no matter associated with it. It's simply a burst of electromagnetic energy. And in the world of radiation, if you guys remember Venn diagrams, so we have nuclear radiation. So nuclear radiation and electromagnetic radiation. We mentioned the idea that these are not the same thing. Nuclear radiation is matter or energy ejected from the nucleus. Electromagnetic radiation is oscillating electric and magnetic fields through space. So generally, when we talk about radiation, these are not the same thing. Nuclear radiation is not the same as electromagnetic radiation, except for the gamma. The gamma sits right in the middle. It is the only type of radiation that is both types at the same time. It is nuclear radiation because it's emitted from an unstable nucleus, or it can be. It's not always, but in the process of what we're going to talk about, we are considering it as ejected from the unstable nucleus. But it is also electromagnetic radiation at the same time. It's just part of the electromagnetic spectrum. So it's the ambassador between two types of radiation. Also of note is that it's just pure energy, so it does not change the nucleus. We'll talk a little bit more about that when we talk about nuclear decay reactions. An alpha particle changes the nucleus when it leaves. It takes 2 protons away, takes 2 neutrons away. It's not the same nucleus that it was before. When a nucleus ejects a gamma ray, it does not physically change in terms of its composition, but it emits energy. And casually speaking, it's really just a way to sort of calm things down. If we take a look at the nature of the gamma particle itself, again, if you remember, this is associated with the atomic mass. This is an associated charge, and it has no mass, it has no charge. It's just pure energy, that's all. So again, no change in charge or mass of the nucleus. And in terms of penetration, gamma rays are extremely penetrating. They will travel through your body, and they won't even, beep, boop, they're through. It takes lead, concrete, lots of water. There are substances that can stop gamma rays, but a lot of times the gamma ray will pass through other substances that would stop a beta particle or an alpha particle. Now the next part, again, I'm not an expert as far as this goes, and I've tried to do a little extra research associated with it. They are very high energy. They're very, very high energy. So the inference to begin with would seem that they could do a lot of damage to your cells as they go through. It turns out they are not as worrisome as alpha particles are in terms of their ability to ionize. Again, I'm not an expert on this, and this course does not profess to be high-level technical stuff. Generally speaking, to the best of my understanding, first of all, it's what's called an indirect ionization, in the idea that the gamma ray interacts with other things that then create things that then ionize. As I understand it, although it can directly knock an electron off as well. So generally speaking, in terms of the interaction I just talked about, it can create beta. We'll talk about that in a minute. And also the type of interaction that it has varies with the energy of the gamma ray. Depending on how energetic the gamma ray is, it will actually do different things to atoms as they interact with it. I think part of it is also the fact that a gamma ray is a neutral. It's not positive or negative, so it's not inherently attracted or repelled from anything in the atom or the molecule. So it has to sort of make a more direct kind of shot. But generally speaking, and again, for details that we will not get into in this video, the gamma ray, while it penetrates way better than anything else does not do as good of a job at ionizing substances as it moves past. Now, when it does ionize them, it's a pretty robust event, but it does not, it won't interact as much with your body as, say, an alpha particle or a beta particle does. And that's probably the best way to sort of leave it. So we have alpha and gamma. And so the question is, transparent physics, why did we skip beta? Because beta is actually a little weirder. I'm not going to lie about it. It's weird. So let's take a look here. The beta particle, actually, on top of the fact that I said we had one more particle, I kind of lied. Beta particle actually has two variants. It has a beta plus and a beta minus. So we're going to talk beta minus first. A lot of times when people just say beta particle, they may just be referring to beta minus. I've noticed in my studies and just interacting with the content, beta plus seems to be sort of the understudy in a lot of regards. I don't know. It just doesn't seem to come up as much. Beta minus, if they don't specify otherwise, if they just say beta particle, you can probably assume they're referring to beta minus. But we'll talk about both of them here because, we're transparent physics. Okay, so beta minus is a high energy electron ejected from the nucleus. So it's an electron, just like the electrons you talked about in chemistry class, but it's ejected at a high speed from the nucleus. Now, if you pause for a minute, that should give you a little bit of concern that I might not know what I'm talking about, because you're going to ask yourself, electron, nucleuses have protons and neutrons. How is there an electron getting ejected from the nucleus? And if you thought that, very good job, because it's a rather confusing issue. Well, how do you get an electron out of the nucleus when there's no electrons in the nucleus? So, how do we get an electron in the nucleus to begin with to get ejected from the nucleus? Now, again, we are going to do a cursory overview of how this process happens. There's a lot more to it, and again, I don't profess to be an expert, but I can tell you the basics. Here's the deal. When we are in the nucleus is always wanting to adjust for stability. And again, for reasons that are not in the context of this video, sometimes a nucleus has too many protons, sometimes a nucleus has too many neutrons. So depending on what it has too many of, it has the ability to regulate itself a little bit. So in this case, if we have too many neutrons, we can undergo beta minus decay. And it's actually kind of neat what happens. You've got, again, a neutron in the nucleus. A neutron is just a neutral particle. Now, when it decays, it actually splits into a positive and a negative particle. And if you had an inference of what those particles would be, you are correct. It actually splits into a proton and an electron. And in the process of doing that, we have conserved charge. So we're not cheating because there was no charge to start, and there is no charge afterwards because the proton has a +1, the electron has a -1, so the net charge has not changed. Conservation of charge, one of our conservation laws. Okay, now there's another little guy that flies off. We're not going to talk about it too much, but this guy right here also zings off for matters of a nuclear consistency, and it's considered a neutrino, technically an anti-neutrino of the electron flavor. We don't worry too much about the neutrinos, but the important part is to note that there's an electron and a proton. Now, the neutron turns into a proton. The proton just continues to hang out in the nucleus. And the electron zings off, and that's the beta minus particle. That's the particle that flies off and interacts with other things. That's the radiation that comes out of the nucleus. In the process of doing that, it does not change the mass of the nucleus because there's a neutron turns into a proton, so the mass hasn't changed. But I do associate this with a -1 charge. The beta minus has a negative charge associated with it, so when we go on to formulas a little bit later, we need to remember that that negative sign is associated with it. So, it seems kind of weird, but neutrons, a neutron turns into a proton. It gains, air quotes, a positive charge. And it can do that because it balances that out by basically taking a neutral charge and splitting it into a positive and a negative charge. And if you find that to be fascinating that matter acts that way, then study more nuclear science. All right. Now, if we look at the other side of the coin, we have beta plus. Now, beta plus is a scenario where instead of a high energy electron getting ejected from the nucleus, we have a high energy positron ejected from the nucleus. Now, you may not know what a positron is, and you wouldn't be faulted for that. You may have heard on like Star Trek and stuff like that, stuff called like antimatter. Antimatter is real. Antimatter is just material, like our regular material, protons, neutrons, electrons, but the charge is flipped. So an electron that we're used to is a relatively small mass, carries a negative charge. There is the inverse version of that, and it's called a positron, which is just like an electron. Everything about it is identical, except it has a positive charge instead of a negative charge. It's not evil. It's it's not like the Spock with the Van Dyke or anything like it. It's just a variant. There's matter and antimatter. Now, we happen to live in a universe that's dominated by matter as opposed to antimatter. Well out of the scope of that video to discuss why that's the case. But the idea is, for now, you just have to realize it's just like an electron, except it's got a positive charge instead of a negative charge. And if you didn't know that existed before, well, there you go, antimatter. It's pretty cool stuff. And so just like the beta minus happens when there's too many neutrons, beta plus happens when there's too many protons. And the situation is very similar to the other one. We have a proton that decays via the beta decay process, and it basically gives up its positive charge. So the proton flips over to become a neutron. The positive charge zings out. If you've been attending to the detail, when I drew the electron, it had an E negative. This is an E positive. That's a positron. Okay, another neutrino comes out. Technically, a neutrino versus an antineutrino. We won't worry about that in much detail. And then there's the neutron. The neutron hangs out. Positive charge gets ejected. So when it's all said and done, we haven't violated conservation of charge. We had a +1 charge in the proton, and we have a +1 charge in the positron. So charge of +1 to start, charge of +1 to end. Conservation of charge is still valid. In both of these cases, again, there is no mass change associated with the nucleus. In this case, because it's a positron, there's a positive charge associated with the event, and I probably didn't specify this before. You can write it as an electron, or this is the symbol for the beta particle. Okay, beta is weird. There's absolutely no doubt about it. It is a weird particle, and it kind of sits in the middle of what we talked about as far as the properties of the radiation. As far as its ability to penetrate, it is better than the alpha particle. It will go through paper. It can be stopped by aluminum, but it definitely is way worse than gamma. So I generally kind of think of the idea that it can pass basically through your skin, like an alpha particle would stop at your skin. A beta could go through your skin, but it probably won't go through your body, depending on where it hits. And again, if it goes in your body, it's not going to go deep into your body. And its ionization ability also lays somewhere in the middle, actually probably closer to the gamma end than the alpha end. I mean, alpha is really the heavy hitter. It hits heavy. Beta particles, again, tend to be less ionizing. Depending on your source, I've seen that they are generally considered to be more ionizing than gamma, though. But they are nowhere. This is the absolute champ. These guys are rookies. That's the pro. But the beta particle is what's considered to be direct ionization because it interacts directly with what it's ionizing immediately. So that's the three types of nuclear decay. Alpha is pretty straightforward. Gamma is pretty straightforward. Beta is more complicated, and we do go through it kind of quickly. But it is kind of neat to recognize the idea that you can flip protons into neutrons and neutrons into protons. And I plan to follow up with another video to talk about what that sort of looks like on a big scale. Discussed a little bit earlier in the lesson was the idea of the neutrino. So there's a little fun story associated with that, and we'll wrap up. But so let's talk a little story time on the neutrino. I don't really talk much about neutrinos in this course. So here's the neutrino's chance to shine. Now the story begins in 1930s. In 1930, we did not have something called a neutron. We didn't know the neutron existed yet, which I think is kind of weird, in historical perspective, to think in like 1930 we didn't know about a neutron, but we didn't. We didn't know it existed yet. So in studying nuclear reactions, there was a guy named Wolfgang Pauli, and Pauli theorized the existence of a tiny neutral atomic particle, and he called it logically a neutron because there wasn't anything called a neutron. He said, well, if the proton's positive and the electron's negative, let's call the neutron, it's a neutral particle, it's called a neutron. And again, the important thing to recognize is there was no known particle called a neutron at the time. So he has this theoretical particle that he thinks is neutral, and he calls it a neutron. Again, I don't know if Chadwick didn't know about this, but Chadwick in 1932 actually discovers what we go on to know as the actual neutron. And it's a neutral particle, so he also calls it a neutron. And again, I'm not sure if he actually knew that Pauli had already used that name, but he called his particle the neutron as well. Again, when Pauli proposed his neutrino, and again, I'm not sure that people really jumped on top of that, so maybe it hadn't percolated to Chadwick at the time. So there was actually two particles being called the neutron. There was one that Pauli proposed theoretically, and then in 1932, there's one that Chadwick experimentally discovered. And that's the one that we actually go on to call the neutron. So what happened to the fact that Pauli called his particle the neutron? Well, there's another guy, Enrico Fermi, who actually had a pretty good sense of humor. And so in 1932, as a way to specify between Pauli's smaller neutral particle and Chadwick's heavier neutral particle, he called Pauli's neutral particle the neutrino, which Fermi was Italian. And so if you sort of translate neutrino into Italian, it's called that's neutrino means tiny neutral one. So it's kind of a joke name. It was kind of like calling it the baby neutron, the neutrino. But it stuck. And the actual particle was verified in 1955. And by then, the term neutrino had been widely adopted for it. So, I don't know. Physics has some funny things in it, sometimes like that. And I think this is one of them. So that's a little bonus story at the end. The story of the neutrino. Share it with your friends and family. Thank you for tuning in to Transparent Physics for this lesson. We got alpha, we got beta, we got gamma, and a little bonus story for the neutrino as well. I hope we've had an opportunity to make physics a little clearer for you.